Dirac equation, the Dirac equation, the very famous Dirac equation. So ये आपके सामने है Dirac equation, आयोटा गामा नौ म्यू डेल म्यू माइनस एम साई. तो इसके मीनिंग हम समझेंगे. देखिए डिराक इक्वेशन जो है वो स्पिनर्स के लिए है, स्पिन पार्टिकल्स के लिए, ख़ास तौर से उन स्पिन पार्टिकल्स के लिए जिनका स्पिन हाफ है, क्योंकि स्पिन ज़ीरो पार्टिकल के लिए हमारे पास में ऑलरेडी एक इक्वेशन होती है जिसे हम बोलते हैं क्लीन गॉर्डन इक्वेशन. और स्पिन वन पार्टिकल के लिए भी हमारे पास में इक्वेशंस अवेलेबल है. लेकिन यहाँ पर स्पिन हाफ पार्टिकल के लिए डिराक ने एक अलग इक्वेशन दी है जिसे डिराक इक्वेशन कहते हैं. तो थोड़ा सा डिस्कस करते हैं टेक्निकल डिटेल फ्रॉम द क्वांटम फील्ड थियोरी पॉइंट ऑफ व्यू. सो यू नो वेरी वेल फ्रॉम द स्केलर फील्ड्स, द theory of scalar fields, you know very well that from the Lorentz transformation, from the Lorentz transformations, when x mu goes to x prime mu, which is equal to this lambda mu nu x nu, okay, it transform the field in this way. Now phi prime x will be phi gamma minus 1 x, or lambda, rather than gamma it's a lambda actually. Okay, so it is the field transformation equation number 1. Okay, we already know that quantization of such field give rise to spin zero particle. Okay, but most particle in nature have an intrinsic angular momentum or spin. Okay, so these arise naturally in the field theory by considering field which themselves transform not trivially under this Lorentz group. Okay, so see, Dirac equation whose quantization give rise to spin half particles, fermionic particles. Okay, so Dirac, as I already discussed, the Dirac equation is for the spin half particle. To motivate the Dirac equation, let's discuss first about the presentation of the Lorentz group, that what we know about this Lorentz group. Okay, and see, so we know that if there is a vector field in electromagnetism a mu, then how a mu transform? We know that a mu, if it's a vector field in electromagnetism, it transform in this way: lambda mu nu a nu and this lambda inverse x. Okay, maybe equation 2. Okay, so in general a field, okay, if you are dealing a general field, so how it can transform? Phi a x transform d lambda a b phi b lambda minus x. Okay, so here index is a and it can be 1 2 3 till n, and this phi a can be a vector, a column vector, and d this d lambda can be matrices from a representation of the Lorentz group. It means that d follow this rule: d lambda 1 d lambda 2 is equal to d lambda 1 lambda 2, equation 4. Okay, so d is a representation of the Lorentz group, and it is obvious that d lambda minus 1 is equal to d lambda minus 1. Okay, and d1 is equal to 1. So see, how do we find the different representation? Typically we look at infinitesimal transformation of the Lorentz group. Okay, so infinitesimal transformation means this lambda mu nu is equal to delta mu nu plus omega mu nu. Okay, so we are writing our lambda in this way for infinitesimal transformation, and we will later on we will study the Lie algebra. Omega is also infinitesimal, and we can apply the condition for a Lorentz transformation. What is the condition of the Lorentz transformation? You know from the special relativity, because to learn quantum field theory you should aware from the special relativity in the covariant form or then the tensor notation. So the condition of the Lorentz transformation is this: lambda mu sigma lambda nu rho eta sigma rho equal to eta mu nu. Okay, and if this is the condition, then you use in the previous equation, then it becomes the requirement that omega should be antisymmetric. So it means omega mu nu plus omega nu mu is equal to 0. Okay, so that is the condition. So this Lorentz transformation condition gives thus omega is an antisymmetric matrix. Note that an antisymmetric 4x4 matrix has how many independent component? You can see that it is as n minus 1 upon 2 independent component. So any 4x4 matrices have only 6 independent component. Okay, which agrees with the 6th transformation of the Lorentz group. 6th transformation of the Lorentz group means there are 3 rotation in the Lorentz group plus 3 boost in 3 direction. Okay, and it is going to be very useful to introduce a basis of these 6 4 into 4 antisymmetric matrices. So for this basis we call them as M A mu nu, with A is equal to 1 2 3 4 5 6. See, and see, instead of using A, we are using some pair of indices. Okay, and with a pair of antisymmetric indices, and we are using antisymmetric indices rho sigma, where rho and sigma can be 0 1 2 3. Okay, so now this base matrices is becomes rho sigma and mu nu. Okay, so the antisymmetricity of rho and sigma means this: m01 is equal to minus m10. Okay, so this rho and sigma is a label of 6 different matrices. Okay, and the matrix is also antisymmetric on a mu nu indices because they are after all antisymmetric matrices. So we can write down the basis of 6 4 cross 4 antisymmetric matrices as this. This is in this way: eta rho mu, eta sigma nu minus eta rho nu, eta sigma mu. Okay, maybe equation 7, where the indices mu nu are those of the 4 cross 4 matrices, and this rho and sigma denotes the basis element which are dealing with. Okay, so rho and sigma for the basis elements, and this mu and nu are for the matrices. Okay, if you use these matrices for anything practical purposes, okay, so we can down the lower or raise the indices depending upon the condition. So this become eta rho mu delta nu sigma nu minus okay. Since we lower the index with the Minkowski metric, okay, we pick up various minus sign, which means that when written in this form, the matrices are no longer necessarily antisymmetric. Okay, means the total form. So see, now in the base, these base matrices are, you can write down M01 mu nu. Okay, now you can write down, when you expand, easily available, that put rho is equal to 0 and sigma is equal to 1 here. So when you put rho is equal to 0, then mu should be 0 only. Okay, and when you put sigma is equal to 1, then only mu is equal to 1 element survive, otherwise it will cancel. Okay, because thus this delta 1 1 element will survive, or eta 0 0 eta 1 1 element will survive. So see, when you put this first element, which is M0000, which is 0, and the second is the element which is 0 rho, and the first column, and when you put this rho 0 and sigma 1, then so just so when you put this, so let's do it again, and after putting the value rho 0 and sigma 1, it is clearly visible here. You can check that it will be 1 0 0 1 0 0 0 0 0 0 0 0 0 0. You can check by hand, by your hand. You can check this, and this also 0 0 0 0 0 0 minus 1 0 0 1 0 0 0 0 0 0. Equation 9. See, the first M01 generates boost in x1 direction. Okay, it is real and symmetric. The second M12 is generates the rotation in x1 x2 plane. It is real and antisymmetric. We can now write any omega mu nu as a linear combination of m. So this omega mu nu, we can write down it is as a half this capital omega rho sigma m rho sigma mu nu. Okay, equation 10, where this capital omega rho sigma are just 6 numbers. They are 6 numbers, and again antisymmetric in this indices that tell us what Lorentz transformation we are doing. The 6 basis matrices are called the generators from the Lorentz transformation. This m rho sigma are called the generators of the Lorentz transformation. Lorentz transformation. And generators obey the Lorentz-Lie algebra relation, which means m rho sigma m tau nu is equal to eta sigma tau m rho nu minus eta rho tau m sigma nu plus eta rho nu m sigma, or the sigma nu minus eta sigma nu and rho tau. Equation 11. Okay, here we have suppressed the matrix indices, means the final mu nu, we suppress that. Okay, a finite Lorentz transformation can then have the expression as the exponential. This exponential is a general expression of omega rho sigma m rho sigma. Okay, so let me stress again what each of these objectives are. This m rho sigma are 6 4 cross 4 basic elements of the Lorentz-Lie algebra, and this omega are 6 number telling us what kind of Lorentz transformation we are doing. For example, they say things like rotate by theta is equal to pi by 7 about x3 direction and run at speed as v is equal to 0.2 in the x1 direction. So that is all about this generators of the Lie algebra we will use in the Dirac equation, and the next version we will see how we define this spinor representation. Okay, so to define the spinor representation we will use the Clifford algebra. Okay, so that spinor representation, the Clifford algebra, we will discuss in the next video, and we will also discuss all the spinors, all the Lorentz groups, etc. thing. After that we will move towards the Dirac equation. Thank you.